thermal fluid sciences experts. This is Pro-Ready Engineer.
Hello, this is Bassam Abdelnabi from Pro-Ready Engineer. I'm excited to share a new video series featuring industry cases. If you like what you see, please consider liking and subscribing. Take care and talk to you soon.
You know, in the high-stakes world of petrochemical processing, it's often the components you don't think about that are the most critical. Today, we're going to dive deep into one of those unsung heroes, a recovery reactor feed cooler. And as you're about to see, this thing is way more than just a simple heat exchanger. It's really an essential safeguard for an entire plant. So, to really get why this matters so much, let's start with a question. In an environment where precision is absolutely everything, what actually happens if the feed going into a reactor is off by just a few degrees? The consequences, well, they're a lot more severe than you might think. And here's the answer. First off, you risk a runaway reaction, and that is a terrifying scenario where the whole process just spirals out of control. Second, you can completely destroy the expensive catalyst that makes the reaction even possible, which just kills your efficiency and your yield. And third, you create fundamentally unsafe operating conditions for the entire facility. So the main point here is temperature control isn't a suggestion, it is a non-negotiable, hard requirement. Now, engineering a solution for this is not exactly straightforward. The team was facing what I like to call a web of constraints, a whole set of interconnected challenges that all had to be solved at the exact same time. Okay, so check this out. The engineering team was juggling 4 big challenges all at once. First, the thermal duty. That meant getting the cooling absolutely perfect. Second was material compatibility, because the fluid going through this thing was super corrosive. Third, the cooler had to meet the rules of 3 different regulatory codes. And finally, the specific TEMA BFU design. That's a U-tube bundle with fixed tube sheets. It came with its own unique set of mechanical puzzles. Let's look a little closer at that compliance challenge, because this is where it gets really interesting. The cooler had to be a pressure vessel, so that's ASME code. It also had to meet the mechanical standards for heat exchangers under TEMA. But then, layered on top of all that, it had to meet API 660, which is basically the gold standard for this equipment in petroleum service. And that standard adds even stricter requirements for stuff like nozzle loads and making sure you can actually maintain it. So how in the world do you solve a problem with so many moving parts? Well, you do it with a highly disciplined 2-part approach. First, you solve the thermal and hydraulic puzzle. Then you solve the mechanical and structural one. Okay, step 1 was all about performance, thermal and hydraulic. After calculating the exact heat load, the team did a detailed LMTD analysis. This is so critical because with the multi-pass U-tube design, the simple formula just doesn't work. You absolutely need correction factors to get an accurate temperature profile. They also engineered in fouling factors, which means they planned for the inevitable gunk that builds up inside the tubes. That ensures the cooler performs perfectly, right up until its next scheduled cleaning. All right, let's move to the mechanical side and see how this all comes together. Here, the ASME code dictates the thickness of every single part that holds pressure. It also sets the rules for welding and what's called non-destructive examination, or NDE, to guarantee structural integrity. And, you guessed it, API 660 adds another layer of rigor, specifying things like how much clearance you need to pull the tube bundle out for maintenance. Of course, a perfect design is completely useless if it's made from the wrong stuff. This brings us to a decision that was absolutely 100% non-negotiable for the long-term reliability of this cooler. The choice here was pretty stark. Standard carbon steel? It would have been eaten alive by the acidic, chloride-heavy process fluid. The only viable option was stainless steel 316L, which is specifically alloyed to fight off this kind of chemical attack. It's a classic case of paying for the right material up front to avoid a catastrophic failure down the road. And here's a key detail. Why the L in 316L? That L stands for low carbon, and it's a huge deal. When you weld standard stainless steel, the heat can cause a problem called sensitization, which creates these tiny weak spots right next to the weld that are just magnets for corrosion. By using the low-carbon grade, that risk is massively reduced, which ensures the welds are just as corrosion-resistant as the rest of the metal. Pretty smart, right? The focus on integrity didn't stop with just picking the right material. Oh no! During fabrication, every single step was put under a microscope. Welding procedures were formally qualified, every dimension was checked, all the welds were hydrostatically tested and inspected, And every single piece of metal was traceable all the way back to the mill it came from. That is what it takes to build with confidence. So after all that meticulous, painstaking engineering, what was the end result? Well, the project delivered more than just a piece of hardware. It delivered a true process safeguard. And here it is, the final snapshot. We've got a TEMA type BFU cooler, built to the highest standards of ASME and API, and constructed entirely from that corrosion-resistant 316L stainless steel. Every single spec you see here is a direct reflection of the demanding, critical role this piece of equipment plays. And the impact? It's really threefold. First, it protects the process by delivering the feed at the exact right temperature every single time. Second, it protects the plant's bottom line by resisting corrosion and preventing those dreaded unplanned shutdowns. And third, its full compliance gives the client total, complete confidence that the equipment is safe, reliable, and built to last. Look, if you take one thing away from this whole explainer, let it be this. A piece of equipment like this is never just a cooler. It is a process-critical safeguard. It protects the reactor, it protects the catalyst, and it protects the entire production train downstream. It's the gatekeeper for a stable and safe process. This intersection of material science, thermodynamics, and strict code compliance is really what makes engineering so vital. To see more deep dives just like this one, make sure you subscribe to the channel. And if you're facing your own complex thermal design challenges, get in touch with the experts over at ProReady Engineer. Thanks for watching.